symmetry is sort of built in. So as soon as you believe the mean field theory, then this particle symmetry is going to be a feature of Boglev-de theory. Here I have to impose it by saying that I don't put any on-site energies, I don't put any next nearest neighbor hoppings. So it's more artificial here, it's more natural in the Boglev-de theory. Okay, but if I have this up-down symmetry of my energy spectrum, that can mean two things. So one thing, if I have a finite energy eigenstate, then it will have a chiral partner at opposite energy. And we have seen an example when we looked at this 10 unit cell topological SSH chain, which is also depicted again here. So we saw that there are energy levels at +1 and -1, and actually they are chiral symmetric partners of each other. So I could pick one of these states, I could apply gamma on it, and I would get one of these states. Okay, so these are chiral partners. But this is not the only option, because if my state is living at 0 energy, then just the fact that gamma acting on the state will also give me a 0 energy state, that doesn't mean that the second state is different from the original one. So for 0 energy states, you can also have that the state itself is its own chiral partner. So the chiral symmetry acting on the state is giving just the state. Okay, so there's no requirement of twofold degeneracy at 0. And well, let's think about these two states. So I have been arguing that this left localized state and this right localized state, they are energy eigenstates at 0 energy. That's also depicted in the spectrum. Now the question, if I take this state, is this a chiral partner of itself or not? And the answer is that it is a chiral partner of itself, because this is described by a vector which is a 20 entry vector. The first entry is 1, all the others are 0. If I just act with such a matrix on that wave function, I multiply 1 with 1, that's 1. So this guy is an eigenstate of the gamma operator. So it's its own chiral partner. Okay, and that's going to be an important fact for the argument which comes now. So there are two options. The more interesting option is when I take a 0 energy state, and if that's its own chiral partner, that's a very interesting thing, as we will show in a minute. Because now I want to go to the question, what happens if I start to go away from this fully dimerized limit? What happens to these edge states? So for the sake of the argument, let's take again this fully dimerized as a starting point. So I have take a long fully dimerized topological SSH chain. Intra-cell hopping 0, inter-cell hopping is 1. And now I switch on a uniform inter-cell hopping V. So I don't introduce this order yet. I just switch on a uniform inter-cell hopping V. Does the 0 energy edge state survive? So I have an edge state on the left end, and I have an edge state on the right end. Do they survive? And the answer is yes, they do survive. They will remain at 0 energy because you have this chiral symmetry, and because of the chiral symmetry, if you have you can look at one edge only, you look at the 0 energy state on that edge, even if you start to continuously deform your Hamiltonian, this guy is its own chiral partner, so its energy cannot start to deviate upwards, because that would mean that also there's an energy going downwards, but that's possible because from one energy level you can only develop a single energy level. So if it would go up, it would break chiral symmetry. So it must remain at 0 energy. So this is one argument, which is showing you that these edge states are protected, let's say, by topology. I mean that by that I mean that as long as you don't change the topology of your Hamiltonian, as long as you don't change the gap, don't close the gap, then those edge states will survive on the left hand, also on the right hand. So chiral symmetry and the presence of edge states in the fully dimerized limit, these two things imply that also if you go away from the fully dimerized limit, you will have those edge states at 0 energy. And they can go away from 0 energy only when the edge states at the two ends are starting to hybridize. So it might happen that, from this fully dimerized limit, when I have a Kronecker delta wave function on the left end, when I switch on the intracell hopping, then I will have an exponential tail. Of course, as soon as the two exponential tails of the two wave functions start to overlap, then they can form, again, a bonding and antibonding state. But that bonding antibonding gap is going to be always small, in the sense that it's going to be, if I make my system longer, then it's going to get smaller and smaller. It's going to get an exponential suppression, this splitting Okay, so it's a fairly strong argument. If I combine chiral symmetry with the existence of edge states in this topological fully dimerized limit, and that's a strong argument that these zero energy edge states are surviving. And surviving, I mean not only that their wave function remains localized, but also their energy remains at zero energy to a very, very good approximation.
Sorry.
Yeah.
Then you are just increasing the intercell hopping, right? So
yes.
What happens if you put disorder?
Yes, I will also discuss that. Yeah. Okay, and so this is illustrated in a finite, again, in a finite sized example here. So I have 10 unit cells in my sample, and I tune V gradually from 0. I set W, so in third cell hopping to 1. Of course, when V is 0, I'm in the fully dimerized limit. So the spectrum looks like this. I have 2 degenerate levels at 0, and I have 9 up at 1 and 9 down at -1. Now I start to introduce this finite V hopping, then I see that my bands get dispersive. So this is what I see from my, these are 9 states which are forming the band of this miniature solid of 10 unit cells. So this is how my band gets dispersive, also down and up. But these 2 states are just sticking to zero energy until the point when their penetration length towards the bulk is getting comparable to the size of the full system. So you see that at this point, for example, you see the example wave functions. So what you see is the wave function itself, so that's a real quantity, so it makes sense to plot it as a function of position. I have 10 unit cells, and in each unit cell I have a black thing denoting, or gray thing denoting the wave function on the A side, and the white thing denoting the wave function on the B side. So this is what you see here. What you see here is that now the penetration length, there's a penetration, so it's not localized on the left and the right, it's penetrating, and the penetration length apparently is similar to the size of the system, so thereby actually this is now a bonding state, this is now an anti-bonding state, so this is now when they hybridize. Nevertheless, they are still localized and still very close to zero energy. Of course, when you do numerical simulations, then they hybridize due to the finite sample size. So this is what comes out from the numerical diagonalization of the Hamiltonian. You get bonding and anti-bonding states. If you look at just a random state in the bands, then that's strongly delocalized. So that's fine. And of course, the fact that these 2 lines, these 2 energy values separate here, exactly around 0.8, V equals 0.8, well, that number is not universal. That depends on how long your system is. So if I would take a 100 unit cell long sample, then this point of deviation would move towards 99% or something like this. So the longer the chain, the more difficult for these 2 wave functions to overlap, and thereby to open a mini gap between those 2 states, bonding and anti-bonding states. Okay, and so at this point we can say that we sort of have a picture of what the bulk boundary correspondence is. I was introducing a very artificial, abstract bulk topological invariant. I looked at the 2x2 momentum space Hamiltonian. I was saying that Hamiltonian is actually drawing me a circle on the complex plane, and this circle either goes around the origin or it doesn't go around the origin. That was the topological classification. And now it seems that if I take finite size samples, then in the boundaries I get some predictions from the bulk invariant what's going to happen on the edges. So that's what is typically referred to as bulk boundary correspondence. You can associate some topological invariants, topological quantities, some topological label to the bulk Hamiltonians, and they will predict what happens on the edges. In this very simple example, they predict how many edge states do you get on the edges, 0 or 1. Okay, yeah.
So if I look at the figure B and C, I see that the energy of the black states is mapped to minus energy of the black states, but for the white states the energy remains the same. Why is there not this correlation for the white states?
I'm sorry, I'm not sure I understand the...
Yeah, so if you look at figure B and C,
yes?
Those correspond to the upper and lower part of your diagram on the left side.
So I take this level, this is twofold, apparently twofold degenerate, there's a very small splitting. I take the 2 energy eigenstates. One looks like this, the other looks like this.
Yeah, and then if you look like on the other curves on your left diagram, they correspond to the site energies in the right picture.
Site energies?
Or you are just plotting the energy values that you have on the right diagram. You are plotting.
These are not energy values.
Yeah.
These are wave function components, amplitudes. Yes, exactly. So this is not the probability, but this is the wave function amplitude, so that's why it can be negative. These are real wave functions, but Hamiltonian is real, so I can just show the wave function amplitudes exactly.
So why is the wave function amplitude for the black sides mapping from plus to minus, and for the white sides it's...
Yes, because these are bonding and antibonding states. So if you think about the hydrogen molecule, it's a symmetric object, and you can try to describe the electronic system of hydrogen molecule by using atomic basis functions. So one s orbital here, one s orbital there, and when you expand the full Hamiltonian in this two-dimensional basis, then you find the tunneling matrix between the two. So if you diagonalize the Hamiltonian, you get that the two eigenstates are this guy plus this guy over square root of 2, and the other one is this guy minus this guy over square root of 2, and that's exactly what's happening here. Yeah. Good. So this is. I think this is the simplest example of bulk boundary correspondence. So you can this concept arises in every sort of more complicated topological solid state models, but this is the simplest example.
You introduced this gamma chiral symmetry.
Yes.
So is there a general way to define the symmetry, because you just put this matrix?
Yes. So the general way is exactly this one. So you say that if you have a complicated Hamiltonian and you are interested in finding out whether it has these properties which are listed here or not, then the task is to try to find a gamma operator which is local and unitary, which is doing this job. In a typical example, it's non-trivial. So you have some complicated Hamiltonian, and usually you don't have this kind of chiral symmetry. But sometimes you can find, even if you have a 16 by 16 Hamiltonian, maybe if you are clever enough, you can find a gamma which will do this mapping. But sometimes you don't find it. Sorry? So that's another thing, that if you have particle hole symmetry and you also have time reversal symmetry, then actually if you combine the two, then that's always a chiral symmetry. So time reversal and particle hole, they are both anti-unitary symmetries doing similar things like this. So time reversal is an anti-unitary symmetry which is mapping the Hamiltonian to itself. Particle hole symmetry is an anti-unitary operation which is mapping the Hamiltonian to minus itself. So there are these three types of symmetries: time reversal, particle hole, and chiral. And if you have time reversal and particle hole, then if you just multiply the two matrices, then you get something which is doing this job, the chiral one. So that's one special case. For certain materials that could work. I mean, certain material, what I mean, if you take a superconductor which is time reversal symmetric, then you have a built-in particle hole, you have time reversal symmetry, and thereby you also have a chiral symmetry. So time reversal invariant superconductors are an example where you have all three of these symmetries. And you can enumerate the consequences of all these symmetries. Okay. Good. And now about disorder. So the key point is that when I was using this argument of the robustness of the edge states against switching on the homogeneous intracell hopping, I was using the argument, I was using the feature of chiral symmetry. I was not using the feature of homogeneity. So that means that if I switch on disorder, as long as disorder is respecting chiral symmetry, it will not dissolve the edge states. The edge states will be conserved. Will stay there as long as symmetry is chiral, as long as the disorder is chiral symmetric. So this is illustrated in these examples. So what we see is that, again, we take this 10-unit cell sample. This is now in the fully dimerized topological limit. So W is 1, V is 0. And we do some random simulation. So what we do, we set the disorder strength to some value. So let's take 0.1, like here. That means that I make random hoppings. So I set some deterministic hopping to 1 and 0. But in addition to that, I also introduce disorder by randomizing the hoppings. So for each W-type hopping, I put a random component with a Gaussian random variable of standard deviation 0.1, if I look at this point. And also, I perturb W and V with the same strength of disorder. And if and for each value of disorder strength, I'm taking a disorder realization of my sample, and I calculate my energy eigenstates. And so that's plotted here. So I take, for example, disorder strength being 0.1. I have these 20 eigenstates. I plot each eigenstate as a dot on this figure. And of course I do this on a very fine grid along disorder strength, and that's why I see a cloud of points. But this is just telling you what kind of energy values do you have in this disordered system. There's also, yeah.
Okay, for the eigenstate, but what about the wave function? Will it be affected by disorder in real space?
Right, right. So it is certainly affected. The question is how much does it stay localized to one edge? And I don't have a quantitative, very precise quantitative picture about this, but the color coding is actually encoding this information. Thanks. So the color coding is shown. So what I do is that I take the wave function. If the wave function is localized to one end, to a single unit cell on the left end, more than 70%, let's say, then I make a red dot. Otherwise, I make a black dot. So red dots are localized wave functions to one edge. And black dots are sort of more delocalized.
And is disorder basically hopping strength? So
this is only hopping strength.
So it's not all V and W, it's V plus or minus delta W plus or minus gamma. That's my disorder. Yes. Okay.
Yes. And so what the key point is because this kind of disorder, the hopping disorder, it respects chiral symmetry, it cannot really affect the zero energy edge modes. At least, as long as the disorder is not comparable to the other energy scale of the system. So what you see here is that here's a flat line at zero energy. You cannot really resolve the mini gaps here. Probably there are mini gaps, but they are small. Even though all the bulk states are strongly affected by disorder, as you see, these guys are insensitive, and because they are red, that means that they remain also localized on one of the edges. And just to illustrate that how vulnerable this is in a real material, I also plot the case when I have on-site disorder. Of course, in a real material, even if you build a chain of quantum dots, or if you take a polyacetylene, of course, there are electric field fluctuations which are detuning the on-site energies from each other. So this is the realistic thing if you have on-site disorder. On-site disorder is breaking chiral symmetry, and thereby it sort of dissolves the edge states in the sense that the energy gets strongly scattered by disorder. So here immediately a very small disorder is bringing your states away from zero energy, which is quite natural. So it is not surprising. What's surprising is that this kind of disorder does not kill these zero energy states being at zero energy. Okay, so this is just a demonstration of robustness of these edge states. If you work with one-dimensional topological insulators or superconductors, then roughly this is the picture which people have in mind, I think, about the robustness. Again, I have to say that the robustness is coming from a number of things. So you could call it topological protection. You could call it symmetry protection because chiral symmetry is needed. So it's symmetry protected as well. And also you should say it's distance protected because it's really protected only if you have a long chain. Because if it's a short chain, then the two edge states are easily interacting and form bonding and antibonding states. Good. And I think I have something like 2 minutes or a few minutes only. So.
Actually, you got so many questions.
Okay.
I already gave you more time.
Do it elastically. Okay. Thanks. So now. This will be the conclusion. Okay, so this is just, I'm just flashing up this sort of periodic table of topological insulators. The key point I want to make is that this SSH model is just one creature in the zoo of topological insulators, but I think it's the simplest creature you can imagine. So it's extremely simple, but still shows you some features of topological insulator physics. And I think in the second talk so this is here. Okay, these are symmetry classes, these are dimensions, these spatial dimensions. I was focusing on one dimension, so that's this column. And I was focusing on a case with certain symmetries, and I mean, symmetry class names are here. I don't want to go into details what they mean. The point I want to make is that this SSH model can be fit into this BDI symmetry class, and that means that its topological invariant is an integer number. So in my case, I was showing this simple SSH model. I had an integer number of 0 or 1, but you can play around and try to figure out, construct more complex models where this winding number is not only 0 or 1, but it can also take larger values. So that's what this Z means, that this topological index for this kind of symmetry class is an integer. And then in the second talk, I will talk about the quantum anomalous Hall effect in 2 dimensions. So that's a different symmetry class. I will tell you which kind of symmetry class and also the quantum spin Hall effect I have plans to talk about in the next talk. Okay, so far, this is the conclusion I wanted to sort of convey. If the bulk has non-trivial topology, then the edge has disorder-resistant bound states. This is often called the boundary correspondence, and the simplest instance of this is, I think, the SSH model. And for the rest of the talk, for this talk, so let's say I'm trying to use like 5 minutes to summarize this project, which is an ongoing research project. It's not really, it's not like proposing some very robust quantum bit for real experimentalists. It's like a conceptual picture about how to use this SSH model as a minimal model for a topological quantum memory. So this is what we call poor man's topological quantum memory. It's protected by this topology, symmetry, distance, but it's poor man's because we don't think it's actually sort of a way to go for real experiments or for industry. And the key message there is that an almost noiseless qubit is obtained by putting together many noisy qubits. So that's the statement, and I'm just illustrating the whole thing with a single figure. I'm jumping over these things. So this is what we imagine, that this is now a thought experiment. So you might want to store quantum information in a charge qubit. Charge qubit is just your electron can live on left or right, and you can form any superpositions of these, and that would be your quantum bit. It's called a charge qubit, and people are doing experiments on charge qubits. Now imagine the very artificial situation when this charge qubit is subject to a very special type of noise, hopping noise, so that you can keep the on-site energy 0, but for some reason the hopping you cannot really control, so it's noisy, it's uncontrolled. It is a random value for all experiments you are doing. And that means that when you encode quantum information into this qubit, the information is going to be lost because there is a random component in the Hamiltonian, and that's going to do some random evolution with your quantum bit. And so that's sort of bad. And here what we are discussing is a system where you use an SSH model, SSH chain. This is now just 2 unit cells, 1 unit cell here, 1 there. Here you build up this SSH chain from the same noisy elements. So again, we assume that we cannot fully control these hopping amplitudes. There's always the same amount of noise as on our charge qubit. Nevertheless, if we could write this information in this 2-dimensional zero-energy subspace of the SSH model, these are robust. These zero-energy states are robust against hopping noise. So even though I build up this memory from the same noisy elements as my original charge qubit, this memory will serve better. It will keep the quantum information for a much longer time compared to the original charge qubit, even though the same amount of noise is put on these hoppings. Okay, and we had some numerical simulations where we tried to sort of illustrate that actually this works. So the key point here is that, let's look at, for example, this graph. So this is the fidelity, so how well the information is preserved in the actual qubit. This is waiting time. And this dashed line is the charge qubit decay of fidelity. So if I just encode in a certain model, if I encode the quantum bit to this charge qubit, then this is the time evolution of the decay. But now if I encode this in the charge qubit, but then I transfer the information to this SSH chain, and then I transfer back and read out, then the fidelity gets better. So this is what is shown here. So the best thing is if you look at this red curve, and this is what you see, the fidelity is getting much closer to 1 compared to this dashed line, which is the charge qubit. So indeed you get a good quantum memory, and the memory has a longer lifetime, because the lifetime was this one, like 10 units in some units. And then if I use the SSH chain as a quantum memory, then this is getting longer. Okay, and so this is the conclusion of the second part, and I will soon stop. An almost noiseless qubit is obtained by putting together many noisy qubits. And this is the last slide that is showing you that in principle there are these ideas about one-dimensional topological superconductors and using braiding of Majorana zero modes for quantum information processing, for quantum gates. And what I'm saying here is that this SSH model is very simple, no superconductivity, no interaction. Nevertheless, you can also come up with sort of braiding schemes which are going to give you some quantum operations. These are going to be protected from noise, assuming that that noise is chiral symmetric. So assuming that it's only hopping noise. So again, this is not a practical way to do a quantum computer. This is just an illustration that even in the most simple, in the simplest model, you can cook up schemes where you can study certain physical features of topological quantum dynamics. Okay, thank you very much for your attention.